Hi and hello everyone. What we are seeing so far is the birth-death queuing systems, meaning queuing systems where the arrivals and departures happen one at a time. So far we have seen few models, so let us continue our discussion on with few more models in this week as well in the next few lectures. The first one that we will see now is what we call it as Erlang's loss system, which is in our queuing notation. If we have to denote, this will be denoted by an MMCC model. Okay. This is the one of the first and also the most famous model that is used in queuing theory and with wide applicability. Okay. For example, in telecommunication designs, where originally Erlang developed this particular model in the context of telephone traffic, right. So, the origin of traffic theory or congestion theory started by the investigation of this system by Erlang. So, this is one of the first model that has been considered by him along with MMC and MMCC. This is a loss system. So, why do we say this is a loss system? As you see in the description, that the arrival process is Poisson process with rate lambda, the service process is also the service times follow exponential distribution, and there are C number of servers and there is capacity of the system is C. So, basically what you see here is that there is no queue happens here, right, because either all servers are busy, then any arriving customer would be lost to the system. So, that is why this is referred to as loss system, whereas where the systems where there is queuing happening like in MM1 or MMC or even MMCK, there is some amount of people can queue, whether it is finite number or we are assuming to be infinite number, there is always a possibility of people queuing up for service, right, customers queuing up for service. So, those are all called delay systems, because they what happens there is that you have customers waiting. So, there is after some delay he is going to get his service. So, those are all referred to as some delay systems as opposed to loss system in this particular case, but here there is no delay happens, right. Even in MMCK model, of course, there will be some amount of people who will not be able to enter into the system, but here it is the case that there is no queuing happens. So, it is a pure loss system, that is what So, that is why these kind of models are all called where there is no queuing happens, right, or will be called as loss system, right. And as we said, this is one of the very first model, and this model can also be regarded as a special case of MMCK if with the k is equal to C, right. You can also look at from that way. If you do that, then what you would going to get is that your lambda n, right, will be equal to lambda for n less than C and 0 otherwise, and mu n is equal to n mu for 1 to C and 0 otherwise, right. This from the MMCK perspective if you take, and then if you get it. So, the state transition diagram will be given by this, where the arrivals happen at the rate lambda in each state, whereas the departures happen at the rate n mu for if the process is in state n. So, like mu 2, mu 3, mu and so on all the way up to C mu. So, there is no further. So, this is the finite state BDP model with these as the rates. So, we can easily obtain now the stationary distribution or the steady state distribution of this particular model by the usual application of this iterative process, which gives you Pn to be this divided by this sum. So, this 1 over this is what will be then this quantity is what is the P naught that you will get. So, Pn can write explicitly in this form. So, which if I use our usual R notation, right, R is the offered load, then you will get this as the distribution, and as you would see that this is nothing but a truncated Poisson distribution, right, this truncated Poisson distribution. Okay. So, once we have this stationary distribution in place, we can again look at various performance measures with respect to this particular system, which might depend on the number in the system. But the most important measure of this particular last system is this probability, PC, right. That means what is the probability that you find the system in this particular state C, at which what happens is that there is no entry of any more customers being allowed into the system, right. So, typical happens, suppose if a telephone line has some C channels or right, or a network which we talk in terms of bandwidth. So, what is the capacity, right. If it is not able to connect, then the call gets dropped, right. So, that is where this quantity will come in. So, this PC, which is basically the r to the power c by c factorial by this sum, which we denote it by BCR, which is what is referred to as Erlang's last formula or Erlang's B formula or Erlang's first formula. We already seen an Erlang C formula, right, in the context of MMC, which is the probability of delay. It is an important measure. Similarly, what is the probability of loss here, right? There, what is the probability of queuing is what you are interested in Erlang C formula, and here it is the probability of loss, right. So, this is what is the probability that the system state would be in C at any point of time. So, this is what is referred to Erlang's last formula and Erlang's B formula, Erlang's first formula. Here, this is all called as the blocking probability. This is what is called the blocking probability. But then there are two notions of blocking here that you need to understand. It so happens that both the notions coincide in this particular case of Erlang last system, right, but it may not be true in general for any other last system. We will going to see one later on where you will see that these two quantities are really different, okay. But it so happens here both this concept of blocking is same as is equal or is one and the same in case of Erlang. So, this itself would be simply referred to as Erlang's last formula. So, what are these notions? One is called time blocking, right. We know PC is the probability that all C servers are occupied at an arbitrary time or the fraction of time that all C servers are occupied. We know from the notion of stationary distribution and limiting distribution, this is what you get when the Markov process has a stationary distribution, and if you start with the Markov process, then Markov process is what we call a stationary Markov process. For a stationary Markov process, this quantities would be given by this probability of the equilibrium probability of finding the system in that particular state, right. So, in that sense, time blocking would be given by this PC for a stationary Markov process by the equilibrium distribution or steady state distribution, and that would then equal to PC. So, PC, that is what we called here, or which is also called as capital BCR as the Erlang's B formula, is the probability that all C servers are occupied at an arbitrary point of time, and which is also the fraction of time the all C servers are occupied, right. This is clear from our knowledge of Markov process that this is what you are going to be interpretation for this, and this is what is referred to as time blocking. Now, there is a notion of call blocking, which is what is important in this particular case, right, in a last system. What you are interested is what is the probability that an arriving customer, right, finds that all C servers are occupied, or that would also be equal to the fraction of arriving customers that are lost. So, we are not concerned about an outside view of the system at an arbitrary point of time. What we are looking at the system at the point of arrival of a customer. At the point of arrival of a customer, what happens to the system is what is more interested in such systems. Okay. That is why this call blocking, when a call arrives, right, what happens to that call? So, what is the probability of this blocking here? Now, here it so happens this PC is also the probability that an arriving customer would find all C servers occupied, which would also be equal to the fraction of time, the fraction of arriving customers that are lost. So, this PC here has now, as you can say, 4 interpretation, right, 4 interpretations as we see here, because time blocking is also equal to call blocking. And why this is, how this is happening? Because of this nature of Poisson arrivals here and the pasta property, right. That is what is giving us this call blocking, making is same as the time blocking in this case. So, and hence totally in such case without any distinction, we will be simply calling this as a blocking probability in this particular case, when there is no difference between this, that one might simply refer to as simply as blocking probability, which is what is given by the Erlang's formula, and this is what is relevant in this particular case. Okay. So, due to importance of this particular quantity in practical problems, in applications, there are readily calculators are available, there are tables available for computing this, the values of this. Okay. There are many calculators, online calculators available. Say for example, if you can look at this site or many places, of course it is available. There are Excel sheets available there readily, like which you can utilize, so on. So, yeah, you can utilize, you can look at this particular thing for an online calculator of this Erlang's formula, right, which is for ready reference, like any other tables that have been developed for in different fields, like in statistics, like there are tables of distributions it is given, right, normal distribution and so on. So, in the same way this is also available, tables as well as calculators to get the value of BCR are available. But the beauty of this result or the significance of this result is because of certain insensitivity property that this particular result holds. Okay. What do we mean by that? We see that this formula, it can be shown later, but we will not be showing it, but it can be easily seen when we see MG type of models, like when you do a similar analysis you would arrive at this particular result. What is that result? This particular form of distribution that we have given here, right, which is the equilibrium distribution in such a scenario is given by this truncated Poisson distribution, right, is true for any MGCC model. What does that mean? That the service time distribution could be anything, and this result holds true, or this result depends only on the mean service time. It does not depend on the actual distribution of the service time, which is a very significant result, because service times being exponential might be a restriction. Now, what you are seeing is this result is true even if it is not exponential. What is needed is that what is its mean, right. So, that means this becomes the form of this distribution, and hence this last formula or Erlang's B formula is independent of the form of the service time distribution. Like whatever be the service time distribution, this formula holds true. Very significant result, and that's the power of this result, right. That's what you call the robustness of the result of this formula, or the insensitivity of this result to the service time distribution. Okay. Now, these two formulae, that is basically by Erlang, which is delay formula and loss formula, or B formula or C formula, or first and second formula, whichever way you call it, are fundamental results in teletraffic engineering as well as in queuing theory, and are still being used today. And this because they specify quality of service to the number of available servers. Okay. As a typical example or application of this formula, or how one looks at different this particular formulas, like both of them plots related to this Erlang-B formula or loss formula, they are one and the same, though we have given two different way, it is the title, just to get familiarized that these two are one and the same. But what is that we are depicting here? Here on the x axis you have the traffic intensity, which is basically the R, and this side is the blocking probability. Now, the different curves represent the different number of servers that we have assumed. Say for example, this blue one represents the 2 server case. So, when you have 2 server, right, and for what traffic intensity that the system would offer, what would be the corresponding blocking probability. Say for example, if I have 2 is the my offered load, right, or the traffic intensity, or the if I have, then corresponding to this would be roughly, right, one can say that roughly this is the blocking probability. So, that means what? If I have 2 server case, if I have 2 server case and if my offered load is 2, then my blocking probability is going to be 0.4, right. Or if I have 4 server case, then this blocking probability would be reduced to less than 0.1, right. If the green line represents 4 server and this red line is 6 servers, this black is 8 and this magenta is 10 server case, right. So, if I want to bound by this, for suppose if I say that 0.1 or 0.01, then what should be my number of servers and that and what should be my offered load, so that I am managing the system within the specified quality of service parameters, right. So, that is what one can infer here. So, this is tells you the how it is going to behave, right. For example, it is expected that when the number of servers increase for the higher offer load, that the blocking probability would be lower, right. But the analysis is not just that much intuition, right. It is a little bit more than that you need to quantify. When you have an exact formula in your hand, whether it is need not be exact, how you can analyze, get the value, then you need to analyze how it is increasing, fine, whether it is increasing like this or it is increasing like this, right. You need to understand everything. So, for which only you need to do this, which what we call analysis. So, the more analysis that you do, the more insight that you are going to get out of the system. Okay. This is one way. This is in a reverse way, right. So, you are looking at the number of channels here, right, and this side is traffic intensity per channel. So, basically R by C is what we are giving it here. It is our rho we can think. Okay. So, this is what we are giving it here per channels to normalize between 0 and 1 is what then you are looking at it. And this different curves gives you what will be traffic intensity that will be generated for number of channels when you fix and the blocking probabilities that you fix. For example, this black one is basically 1% blocking probability. Okay. So, if I have say for example 4 servers, right, then this is the black is the line of 1% blocking probability. So, for the 1% blocking probability, if I have 4 servers, then the traffic intensity per channel would be roughly about 0.2, right. So, this one can look at where it can reach at this level. Say for example, for this level with the 15 in hand, I can go in this plot only up to 20. Like if we go beyond that, then you are going to see that you will not be able to, it will be exceed 1 in a way. So, that it is not going to be stable in a way, right. So, this is what same thing, but we are looking at in a different way as a function of channel and traffic intensity, like where will this 1% or this blue line is now 15% blocking probability curve, right, and what would be the traffic intensity that we get. So, if I want to see like how much traffic I can put, if I want to keep within this particular blocking probability level, right, and as a function of number of servers, then I can look at this particular graph. Okay. Suppose if I decided say 10% is my blocking probability, then I will look at this pink curve, and depending upon what is the number of channels, like what would be the maximum traffic intensity that can be achieved, that I can push inside the system, right. That is what will come out. So, that this blocking probability is within that level, right. Otherwise, the blocking probability will exceed that level. That is what you gain. So, like this different kind of analysis, like depending upon the same formula, like you can do with respect to this particular formula. And we just depicted here just because of the importance of this formula, but a similar kind of analysis can be done with respect to any performance measure, and that is what is all about performance analysis. Performance modeling is that you take a system, you create a model and get the quantities. Performance analysis, you do this. This is up to you, like what kind of analysis that is required to be done and what you wanted to do, like you can carry on with this kind of things. Okay. Now, some remarks are in order with respect to this particular model. So, while R is the offered load, this is the carried load, because you know that PC is the fraction of arrivals that are lost, or load that is lost. So, 1 minus of this would be the load that is going inside. So, R times of this would be the carried load. Okay. So, another quantity which we call is throughput. This is defined as the rate at which customers depart from the system after being served. Obviously, after being admitted and served, this is given by this, because out of this lambda proportion of customers who are arriving in a Poisson fashion, right, PC is the fraction of customers that is lost, right, again because of this call blocking idea, right, not because of time blocking ideas here, right. So, that is 1 minus BCR. So, this lambda times this would be the throughput for this system. So, this is the rate at which customers are accepted for service, and these two rates must be equal in equilibrium or in steady state. So, rate at which customers depart and the rate at which the customers are accepted for service, both will be equal to lambda times 1 minus PC. This is what is given. Okay. And as we said, this is a loss system, and in a loss system, sometimes such as this particular Erlang loss system, this kind of wordings are used. So, which you need to get familiarized, which is basically this is a system which is referred to as a system with where blocked calls are cleared. Okay. They are not in queue. The moment you are not able to get access to the server, you are lost, you are cleared, like you are out of the queuing system, right. So, that is as opposed to delay system. So, that is where the way delay means where you are kept in, you are being kept in the system, but with a delay then you will be able to access the server. In loss system, the blocked calls are said to be cleared. So, sometimes it is also referred to as a system where blocked calls are cleared. Okay. So, the expected number of busy channels, there could be many performance measures further that you can obtain, just like any other model that you are handling. But in this particular case, this is also important, that expected number of busy channels equals the carried load, which means the expected number of busy channels would be equal to this, R times 1 minus B is what then you would obtain. You can show that, right, and hence the expected number of idle channels, right, C is the total number of channels. So, the expected number of busy channels is this, right. So, how do you compute this? As you know, prove this I said, like you can look it up, or otherwise you can simply you have the distribution of what is the probability that number of channels n, some 1, 2, 3, 4, 5 number of channels are busy. So, what is the number of channels busy, multiplied by the corresponding probabilities will give you this. Okay. Now, this quantity is the free channel. So, C minus the expected number of busy channels will give you the number of free channels, right. These are all performance measures that you would talk with respect to this particular system. As usual, you can also determine what will be this L, LQ, W, WQ and so on for this system in the usual manner. And again, all these quantities, for example, throughput, carried load, or busy channels, idle channels, everything you can look at in terms of parameters and analyze deeply, so on. So, this is we are saying for every model it is possible to do, and that is depending upon the requirement that you will be doing that. Okay. But this formula, if you look at carefully here, right, you need to compute this PC, you need to compute this and this sum, which involves a critical quantity which is C factorial, right. But as long as C is very small, you can directly compute C factorial, right. But as you know that if C is a large number, then this factorial itself cannot be handled by computer within its capacity, right. So, you need to find a way of getting this computing this factorial, right. As you know, like 170 or 170, if it crosses, then you are running into trouble. But many real life applications have large value of C, right. The capacity, telephone line capacity, if you think R nowadays in a place where the call centers are there, 200 lines is not a uncommon phenomena that you might find in a big call center operations, right. So, this C, which is number of channels or number of servers, right, are assuming large values is not an uncommon phenomena. So, one needs to handle, but in that case this for direct application of this formula runs into trouble, or it will take long time even if it is doable in a complicated way. But we can always find an alternative approach to use to compute that BCR. One such approach relies on the iterative relationship that one can develop with respect to this BCR. Okay. This you can again prove this, we are leaving it because these are all not very complex ones, which you can prove that what is the relationship that we are looking at it, which is typical in any computation that you want to try to do. You always aim for an efficient way of computing, and to do that efficient way of computing often you might want to use certain iterative procedure. So, in this case it so happens that BCR is related to BC minus 1R in this relationship. So, you basically take up this and then take up this side and show that this is equal to the left side, right. You know what are these quantities and so on. So, you can just see that this relationship will be hold. With the initial condition B0R is 1. So, you start with B0R is 1, right. So, then B1R you can compute, B2R you can compute and so on. So, you can compute for the same R. The required number of servers C could be 1000, you can easily compute it very easily, but whereas directly application using that factorial function would be very difficult to implement it, right. So, this is the relationship that we can use it to compute. Say for example, this is a very simple one, but you can go further and see like how much you can go. Lambda equal to 6, mu is equal to 3, C is equal to 4. So, you want to have the fraction of customers blocked, you want to compute for this MMCC or MM44 model, and R is 2 here. So, basically we want to compute B42 is what this quantity would be. Now, if I use this iterative process, right, I start with B02 is 1, that is the initial condition. B12 I just substitute here, right. How do I get? R is 2 times 1 divided by 4 times plus 2 times 1, right. So, you get here 2 by 3 and use this in the next computation using the same relation to look at B22, B32 and B42. So, n number of computations that you can do, you can arrive at the corresponding blocking probabilities that you can compute, right. Just simple example that you can do. Of course, for the same system you may have other question that you can answer it also through the other performance measure that you might develop. Now, what is the relationship between these Erlang-B and C formulas, right. This BCR can also be used to determine the performance measures of the corresponding MMC model, meaning that if there is no loss, means everyone is admitted into the system, that is MMC model. Now, recall that my CCR is basically the probability of delay in an MMC model. Okay. Now, this CCR can be computed from BCR using this relationship, and this relationship can also be proved by looking at the quantities. There is nothing much here actually, right. So, B and C formulas are related to here. Now, once I have this BCR computed, then I can compute this CCR very easily, and this CCR is what is the probability of delay or Erlang C formula that you might be interested in this, right. Very related to this loss system. Also, for the MMC model, you have other quantities like L, LQ, W, WQ. They all can be expressed in terms of CCR. Say for example, LQ would be given by this expression or this expression in terms of CCR. So, once I have this CCR, then my LQ is this L, W, WQ, everything you can obtain through this. Now, LQ I have obtained it. Now, I know what is my WQ, what is my W, and everything using this itself, using our standard relationship, one can easily obtain it here, right. Say for example, in the same example, if you want to compute C42, what is the probability of delay, right. This is the previous one says this is the probability of loss, the blocking probability is what, this B42. So, the corresponding C42 would be, if it was an infinite capacity queuing system, a delay system as opposed to loss system, then what would have been the probability of loss, right. So, that is a probability of delay is what this one is, right, 4 by 23, and LQ in this particular case it so happen is also equal to 4 by 23. I can compute L and so on for the corresponding one. So, this is also relationship which can also be exploited to obtain the quantities related to Erlang using for the C formula or corresponding MMC model, right. So, this is the loss system that we have seen. Now, what we will see next is again this is a no queue system, but this is not a loss system in a way, but this is called as infinite server queues or queues with unlimited service capacity, right, which is we denote it by infinity, which means there is infinite number of servers. This is basically a self-service system, if I have to say. This could be something like there is a radio broadcast going on, and then the number of customers who want to listen to that particular broadcast, right, pretty much everyone can listen to that, right. So, there is no need to wait that before you listen to that, right. Similarly, suppose if there is a TV show which is being aired and then you are watching the TV show, right. So, pretty much everyone on the earth, if you want to watch, they can always watch, right. So, that is what in self-service model is what in a system that can. So, this model again can be modeled using a birth process with these rates, where arrivals are happening according to a Poisson process. Do not ask me like whether people who are tuning into a particular radio show, they will arrive according to a Poisson process, right. So, that is the critical question, but if it is so, if the data shows that people tuning in according to a Poisson phases, then this model is applicable, and they listen to the duration, they listen to an exponential amount of time, again this M can be questioned. Like this every assumption can be questioned, but under the assumptions the model is true, right, and we have a BDP for this, and that will have this particular rate that you have here, right. And the steady state system distribution in this particular case using our usual approach can be obtained to be this distribution where Pn naught is e to the power minus r. So, ultimately my Pn is this one, which is again as you see is a Poisson distribution with parameter r. Now, you can see relate to MMCC model where C tending to infinity, what would have happened, right. So, that is precisely there you had a truncated Poisson distribution. So, here you have a Poisson distribution is what then you have here, right. So, this is what is the steady state distribution. Now, here once I have this, I can obtain the usual performance measures for this particular case, which are given by these particular quantities, okay. And this Poisson distributed system size distribution holds true for an MG infinity queue in general, and this is the robustness or the insensitivity result concerning this infinity model. So, in this particular case what happens, this particular distribution is true as long as the arrival process is Poisson. Now, you know that listeners listening to a constant amount of period only, still this will be the one, but as long as the arrival has to be Poisson, right. So, you have a partial result or partial confirmation or confidence boosting measure with respect to this particular form of the distribution that you might arrive, right. So, this is true for MG infinity model. So, this particular steady state distribution which is Poisson with parameter r is true as long as the arrival process is Poisson, and it is insensitive or independent of the service time distribution. What is required is the mean rate. What is the mean service rate is what is it will be depending upon, which is from there only you are going to get mu, right. So, this is true, and this is what you have here with respect to this infinite server queue. Okay. So, we will possibly end here in this lecture. So, we will continue with some more type of models in the next lecture. Okay. Thank you. Bye.